So this talk is a little bit like technical. There is so many details because of the topic relatively new. So we will probably go in like quickly through the slides, but we are absolutely confident that this audience is prepared, so you will be able to follow pretty well. So what is this talk about? So like a disclaimer. So the first and foremost, so it's something like about doing like stealthy attacks, not like we know in Ukrainian power grids when the attacker just targeted the piece of equipment. So it's usage of the industrial protocols, and it's about what the attacker actually need to know in order to be able to execute such attacks, and with a key takeaway for basically for the defenders, so that we know what the attacker needs to do, so that we know how to prevent him from doing those bad things. So like, how many times all of you have seen a scenario like this? So many demos on the expos and at the conferences where a small-scale system is taken down by modifying a packet or two. And then typically it is something like it is assumed, the most frequently assumed scenario it's trying to achieve via man in the middle. You hijack some traffic, change something in the payload, and things go nuts. And one of the reasons why we basically believe that man in the middle is one of the most important threats for industrial control systems is because, the protocols are insecure, no authentication, integrity protections, because the mechanics of man in the middle attack is very well understood and we know exactly how to do it. Tons of tools are available, plug and play. And thirdly, because we simply don't know better yet. Yet is here, actually, I already know, but it's not a part of this talk. So the reason why they like those systems fail spectacular in intended way in the small-scale testbed is because somebody who designed that attack, for illustration, they know the system very well, so they know what to change. But how does the industrial packet look like to the attacker when he does not know the system? So this is, for example, the communication of the turbines in the nuclear power plant. To begin with, we can't even see the payload because, well, it's a proprietary protocol. We don't have parsers. Well, we know that. So that's, of course, problem number one. But there are a lot of open protocols in industrial. So let's see what the attacker will see there. So Modbus 1 and 0 probably on-off states, but could be all status data. We don't know. BACnet, you see some numbers. Well, some numbers we can guess because it's BACnet. Something can be humidity, temperature, but then at the bottom we have 1087, like what on earth could be that big? So this is a floating point, and the value ranges from 3 to 71,000. I have no idea what it could be. Next is, like something in the range of 100, maybe temperature again, maybe percentage in our range, we don't know. DNP3, again, does not look to me like frequency of power, but it doesn't look to me even engineering units. So as you can see, the more we look into this packet, we understand the data is not really meaningful, and it does not really indicative immediately to the attacker on what he can react upon. So another DNP3 packet, like when I see 56, I start thinking it could be frequency, and maybe these are engineering units. But what is 17? Like donuts? Donuts per hour?
Squirrels?
So it could be, the first question we have to start asking us, is it a direct measurement or is it the result of computation? We don't know. The next question to ask, what are the units? Is it bit counts? Is it percentage? Is it engineering units? We don't know. If it is those are engineering units, let's assume we could determine that, others measuring length, temperature, flow, pressure, and so on. So we can keep guessing till tomorrow. So in order to understand what the data, basically what defined the data, and in order to develop ways to be able to interpret the data, because this is what the attacker needs, we need to understand actually point configuration. So the most we know all the Purdue architectures, that at the lowest level we have raw data, and when the data traverse to the higher levels, we extract information from raw data, and then we already have some process data, which already losing a lot of information which was initially collected at the bottom. Let's look how, so basically, the way how the data will look like will be defined by the point configuration. Everything that could be set or measured in industrial control is called a point. So when an engineer configure a point, first and foremost, he has to calibrate the sensor. So the sensor can measure over its engineered range, but we typically scale it to measure what we need. Then the second word is the engineer has to set up low and high limits, which indicates that the process is in suboptimal or unacceptable conditions. So the electrical sensor signal will be scaled into basically transformed into the proportional, for example, current signal from 4 to 20 most typically used. And then it goes into input-output card, and that will be mapped, basically converted by the analog to digital converters into the decimal number. So, and then eventually that measurement will be presented as a decimal number, for example, in our case, 12-bit resolution from 0 to 4095. So this slide just shows okay, we measured something, converted, and then we get, at the end, we will get bit counts. So this is what you see right now. It's called raw data. It is not useful data at all to anybody, not even to operator or engineer, because it does not carry the context in which it was captured. To be able to understand what the data mean, you need at least know, and that the minimum amount of information is a range. So, but again, when we look at them, it carry no information. So eventually, these raw bit counts will be transferred, translated basically into the engineering units, but that won't be even necessarily the same units in which it was measured, because the operator will have different requirements, and through the formulas, they can be translated in completely different units. So, and the point is that depending on the configuration of the system and depending on the industries, for example, process control or substations, sometimes the raw data will be scaled already at the HMI and sometimes on the controller. So what the attacker will see in the packet, it could be both engineering units and bit counts. And we will see that the substation, you will typically see those no-name counts, which tells nothing to the attacker. So, and if we dig a little bit deeper into this, so you see, in our case, in our example, we have that this 4095 counts, they are scaled this value from 4 to 20 milliamps. But typically, or often, the engineers want to also being able to detect underrange and overrange. So then they will select a specific range, for example, from 0 to 21 milliamp, and then this will be all used to translate counts. So basically, in order to be able to reverse engineer the number, you will also need to know the offset and overrange. So basically, there are so many cases how data will be scaled, is that, for example, when the vendors build equipment, they already pre-build multiple possibilities to scale according to the tremendous needs of the industry. So now, Chris will tell you how the data points are configured in the power grid.
Thanks, Marina. So my background is electrical engineer. I used to work for a power company. And one of the key things that we had to deal with all the time is just configuring the data points. And that could be a job in and of itself. So let's give an example of a power line, 115 kilovolt power line. Well, how do we translate that data down to the electrical world, into the digital world, and then present it to an operator? But remember our context. If an attacker is looking at this information and they don't know all these different components, like a current transformer and a potential transformer, and the ratios, then they're not going to know how to do a stealthy, like a Stuxnet style attack where they won't be detected, instead of just blinking the lights or doing a denial of service. So we bring these measurements down to a transducer. You got to know the type of transducer. This whole process has to be completely engineered. They turns the AC signals into a DC signal, which is interpreted by relays, panel meters, the RTU, HMI, and it's presented on the screen. You also have to properly select your CTs and PTs for percentage overrange, because you don't want it to read 115 kV, and anything above that, it flatlines. So we don't want to do that. We want to have all that overhead range. So here's a Purdue model showing the data flow from level 0 at the sensor level. So in the substation we have CTs, PTs, and other things going to a transducer or RTU input-output card, going to the front-end processor, going to the SCADA master, up to the SCADA historian, and even up to outage management systems. So let's look at level 0. So there's a picture of a PT and a CT. How many people have been in a substation before? Okay, good. So you've probably seen these before. The great thing about them is the equation for all of this data transfer is basically a linear algebra. Y equals mx plus b. So I won't read the calculations. So if we know the CT ratio and the PT ratio and the transducer multiplier, and if it's the transmission line is line to line or connected line to ground, then we can calculate how many megawatts that the line can read. Then let's just say our transducer reads from 0 to 1 milliamps. So now we see 0.25 milliamps. If I take an amp meter at the transducer, we know that it's reading 90 megawatts. And a substation technician has to do this every day. And again, once you transform that data from level 0 to level 1, it's going to be in a different format, a different size database. So you may have a 16-bit analog digital converter that has counts. So 90 megawatts is 8192 counts, and so on and so on. Level 2, the SCADA database may have to talk to many types of RTUs with many different protocols, many different protocol sizes. So you might have 12-bit analog on, say, Telegear 8979, or 16-bit analog with DMP3, or 32-bit accumulator as well. So the SCADA database is going to have a lot larger bucket to store all this information. And so the scaling in the database, you'll see a very large number at the bottom, but that doesn't make it easy to understand that it's 90 megawatts. So when you're an attacker sniffing at each one of these levels, if you've already gotten access to it, you're going to see 512, 2560 counts, or that large number there at the bottom. It doesn't make any sense. You lack the context. So how can you do a stealthy style attack against that? Well, we've got to reverse engineer the process data. And traditional exploitation of the IT tools can get us access to the IT systems where we store the configurations. They might be in a SharePoint or in some kind of a shared folder environment. But the post-exploitation engineering attack tools, you have to use your calculator to figure out, the physics of the grid, how you want to initiate your attack and achieve your goal. Obtaining the the SCADA data point configuration is the easiest way to understand that. So to get that context, an attacker will want to get after the RTU database or the RTU configuration, the front-end processor, and relay configurations, any meter configurations from servers. Marina, you went to the 27th Chaos Communication Congress.
Yeah, so you see, sort of, for example, if you will try to fetch the config from the embedded devices, sometimes you may be able to log in, and kind of see some numbers, but sometimes it will be already compiled binary, and so it will be proprietary compiler, and we don't even have disassemblers for them, so it's very difficult to build customized disassemblers, but it's not impossible. So, for example, Felix Lindner presented why he built a compiler for Siemens PLC's binaries. So it's possible to do that. But because of the multi-vendor culture, it doesn't scale. This approach doesn't scale because you will have to develop custom disassemblers for a wide range of equipment. So basically, getting config from these low-level devices like RTU and so on, it's really not a good approach. So the attacker is likely, and this is what we are trying to explain, that where the attacker is likely to go, he will go to the servers or engineering workstations.
And like Marina pointed out, in some countries you may have a power grid substation that has all Siemens equipment or all ABB equipment, or like in the United States, it may be every kind of vendor you can imagine with all different ages of equipment. So an attacker is really going to have a challenge getting this context, and it won't scale very well. So here's an example of an RTU configuration program. It's not easy to get. It's not publicly available. You actually have to be a customer. You only can get access to it in a trusted way from most of the real SCADA applications. The other thing that's really interesting is that it's not easy to learn. It's very complicated. There's a lot of things that you have to set in these devices and in the software. So often you have to have a large manual, and you have to take several weeks of training and have several weeks of experience just to get to learn how the context works in these configurations. So an attacker will have to learn this. And here's an example. It just shows, okay, we opened up the database in this RTU, and you see line 1 megawatts, megavars, kV. Now we understand what those point lists in DMP3 means. Now we know that point 0, that 17 is line megawatts. So until we knew that, we didn't know what that number meant. Here's some more examples, screenshots from an example configuration tool. One of the things that I built when I was at the power company, we had so much trouble having a complete understanding of the entire data flow from the power line, CTs and PTs, all the way back to the SCADA master. We made a spreadsheet, and it allowed you to calculate every step. So it was helpful for us as engineers, but guess what? This data is also helpful for an attacker. So an attacker can get that context if you have this kind of a tool. This was very helpful in us helping us troubleshoot, so an attacker could easily use that. So jackpot, that go down the casino. I'll turn it back over to Marina for a slide.
So you already realized, so basically point configuration is complex, and you need to catch, like basically the attacker has to grab a lot of parameters in order to be able to do this, to reverse engineer the mass. But then let's look like what it actually takes to execute cyber-physical attack. So on one hand, like obviously, it's an obvious thing, you need to manipulate the process. But the problem is that there is another task the attacker needs to achieve, is that to prevent response. Control system and the humans are designed and are there to bring process back as soon as it starts deviating. So you kind of have to deal with that, like prevent, suppress alarms and so on. But also within this manipulation of the process, there is one more task to do. The attacker needs a feedback loop. Once you start changing the process, you need to have feedback loop to be able to monitor, is the process moving in the right direction? Do you achieving your goal or not? So suddenly it's become not a one data flow or two, but it's becoming many data flows, and all of them are configured in individual ways, individual pieces of equipment. So you have to grab a lot of configuration files. So complexity grows. And from my experiences, getting like this feedback loop is one of the hardest tasks, and this is what most likely attacker will be failing. And suppressing alarms can be not easy as well. Manipulation is relatively easy. So
yeah, a state estimator is in the power company. In case SCADA goes down, they have a way to estimate the actual flows of the power grid. And I'll speak quickly. You have physics. You cannot fool physics. Current law applies anywhere. So if you try to do an attack, negative 666 megawatts, well, guess what? As an attacker, you forgot to change the other end of the line. The other substation has that same reading. And guess what? The state estimator has that information too. Ruben Santa Marta had a really good state estimator hacking paper, if you want to refer to this later.
So the point is, even if you will be able to manipulate, let's say you figured it out, it's not always that the physics will play along, and there is also systems to detect the basically inconsistent status of the process. So the other problem is for the attacker, and this is again, there will be very difficult to overcome for the attacker, even though you can change the process. So the process was designed and calibrated to measure within specific range. And you, as an attacker, you start moving the process outside of that range, so the sensor will not be able to measure applications I'm losing mic. So, and like, for example, data scaling, one of the most difficult problems for the attacker, if you look at the blue numbers, is that typically when the attacker is probing the process, he's making small changes, but they will be most likely lost in translation. So you're looking, observing, like in a feedback loop, you're trying to see whether the process is changing, and you don't see those small changes because they were lost in translation. And you basically sit there in uncertainty. Is the process changing or not? But you're basically not getting the feedback. So, and of course, there is many more jackpots. So, for example, to overcome all of that madness of multi-vendor, if there is an OPC in the system, you want a jackpot, because that is a super powerful protocol which allows you to enable you with super rights. You can do right into the controls, you can change things, you can query process data, monitor alarms. You basically got one point where you can achieve all the tasks. And it is relatively weakly protected protocol, and it is open protocol, so it's easy to develop exploits for it. So they need to be protected. So the point is that there is this like hijacking the data flow and basically redirecting through your machine. Yes, it is man-in-the-middle attack, but then you need to do all of that, basically you have still to engineer attack, and this is when this attack is becoming man-in-the-SCADA. And
so our key takeaways, there are real threats in the ICS, that we know this, they're coming after it, we've seen it, and there's probably attacks that we don't know about. To do a stealthy man-in-the-middle attack requires that engineering context, and it involves extensive reconnaissance and specialized knowledge. So just kidnap an engineer. If you try to kidnap me, my wife will come after you, and you're probably not like that. So everything that's marked as a jackpot is got to be protected. So segment, lock away your config files, monitor access, harden your SCADA servers, upgrade to secure protocols. Security MP3 is being one of them, or monitor your networks, doing network security monitoring, and finally, have an incident response capability. Thank you. Catch us in the hallway.